Dear students, I am Mahesh Javalkar from Marathon Polytechnic, and today I am posting my third video on analog electronic circuits, in which we are going to cover the first chapter, that is power supplies. And in that, today in this video, I'm going to explain what is a filter and what are the types of filters. Okay. So if we see the outlines of this presentation, in the first point, I'm going to tell you need for filters in power supplies. Second point is a definition of a filter, that is, what is a filter. Third is a block diagram of filter with waveform. Fourth is main components of filters. Fifth is working of a C filter, and sixth is working of pi filter. So C and pi will be the two types of filters what we are studying. Okay. Now here the filter what you hear that we are going to use in power supply is different from the filters what you use in communication. So that difference you should know. So in a communication, we use a filter which will see that certain frequency band is passed and certain frequency band is blocked according to the application. Okay, so it is a frequency selective network in a communication what we are going to study. But what we are studying here, these filters are filters which will remove the AC component, the ripple contained at the output of the rectifier, that will be removed, and the output of rectifier from pulsating DC will be converted into pure DC by this filter. Okay. Now here, first point we will see, why do we need filters in power supplies? Okay. So here if you see that the need of filters in power supplies have come because, okay, the ripple in the signal, ripple means the AC component in the output of rectifier. So output of rectifier, generally we say it is DC, but there will be some AC component present in it. That AC component present is called as ripple. Okay, the ripple in the signal denotes the presence of some AC component. This AC component has to be completely removed in order to get a pure DC output. So we need a circuit that smoothens the rectified output into a pure DC signal. Okay, that means from a pulsating DC, which was the output of a rectifier, if you pass it through a filter, then it will become a pure DC. Okay, a pulsating DC means DC with some AC components is called as pulsating DC. That if you pass through a filter, it will become a pure DC. Okay. Now, if you see the definition of filter, if you have to define what is a filter circuit is one which removes the AC component present in the rectified output, that is rectifier output, and allows the DC component to reach the load. Okay, so the filter is a circuit which will eliminate or remove the AC component present in the pulsating DC output of a rectifier and allows the pure DC to reach the load. Okay, that is how you can define a filter. Then if you see the block diagram of filter here, so here you can see you have shown a block of filter, and then you have shown the input or a rectifier output, and output is a straight line. So here if you see the rectifier output, whatever is there, here you can see this rectifier output is your output of a full wave rectifier. Say this is output of a full wave rectifier. You can see only positive half cycle. This is a plus, 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 plus. No doubt this is a unidirectional voltage, but it is having a AC component in it. It is having a AC component in it, which is called as ripple. So it is not a pure DC, it is a pulsating DC. So here you can see it is a pulsating DC. It is not a straight line. It is showing you pulsating DC. Okay. So this should be converted into a pure DC like this. Now here if you see, this will be the actual VM value, and this is your DC. Okay, direct current. Okay, so a alternating quantity, a pulsating quantity is converted into a pure quantity. Okay, So here the output of rectifier was a pulsating DC. So here whatever we had was a pulsating DC. And here whatever we have is a pure DC. Okay, so this is an ideal filter output what we have shown here. A straight line should come, it should not be pulsating, it should not contain any AC component in it. So whenever we have an output of rectifier, actually a rectifier will convert AC to DC, but the DC what we get at the output of rectifier is not pure DC, it is pulsating DC. Now if you want to convert this pulsating DC into pure DC, then you have to use a filter circuit as shown in this block diagram. Okay. Then we'll go to see what are the main components used in filtering action. Okay, the main components used in filtering action are inductor and capacitor. So here you can see inductor and here you can see capacitor. Okay. Now the statement made for an inductor is an inductor allows DC and it blocks AC. Okay. Now, how you can justify this? Okay. So, if you see a inductor coil, okay, this is a coil which can also be called as a choke inductor coil, and when the current is flowing through it, current will flow with some frequency. F will be the frequency. So the current will flow through this inductor coil. Now this inductor coil is going to provide some opposition to the flow of current. Now that opposition provided by an inductor to the flow of current is called as reactance. And reactance will be given as XL. XL will be the opposition to the flow of current provided by inductor. This is given as 2 pi FL. Okay. Now L is the value of this inductor. F is the frequency of the current and 2 pi is a fixed value. Okay. So 2 pi into frequency into inductance value will give you the reactance provided by the inductor in ohms. Okay. Now here if you see, if the quantity is AC quantity, then this frequency will increase. This frequency increases. If the frequency increases, the impedance also increases because it is directly proportional to it. That means if it is AC, AC will be looking like this. Okay, so in AC, you will be having a higher frequency. Frequency will increase as you go for an alternating quantity. That means the reactance opposition to the flow of current provided by inductor will increase. That is why it will block AC. So this statement here, whatever you have given, it blocks AC is true. Okay. Similarly, if you come for a DC quantity, then DC quantity is like a straight line. It doesn't have any frequency in it. So the frequency will be almost zero. So if the frequency is very less, then the reactance provided, that is 2 pi FL, will be very less. And that means that it will not oppose the flow of current. That means inductor will allow DC. Inductor will allow DC. So what statement you have given here is allowing of DC. This is allows DC. Okay, allows DC. So inductor allows DC and blocks AC. Allows direct current and blocks alternating current. Okay. Similarly, if you come for a capacitor, if you come for a capacitor will be connected, let us say. Now the current is going to flow here with a frequency F. Okay. Now, if you see the opposition to the flow of current, opposition to the flow of current provided by the capacitor will be given as XC. XC will be equal to 1 upon 2 pi FC. Okay. Now, here if you see the relation of the reactance, this reactance and the frequency is inversely proportional. They are inversely proportional. That means if the frequency increases, the reactance will decrease. And if frequency decreases, the reactance will increase. Okay. That means for AC, where the frequency is more, the reactance, the opposition to the flow of current provided by capacitor is less. That means it allows AC. It allows AC. So here the statement says that it allows AC. This is correct. Similarly, for DC, the frequency will be very low, almost like zero. If it is very low, that means the reactance is inversely proportional to it. It will be very high, and therefore the DC quantity will be blocked by the capacitor. Okay. Now here, if you want to make the DC quantity to flow to the load, DC quantity to flow to the load, and AC component if you want to block, then if you are using an inductor, it should be used in series with the load, and if you are using a capacitor, it should be used parallel with the load. Okay. So then we will go to see what do you mean by the first type of filter, which is called as capacitor filter. Okay. So here if you see, the input is given from a rectifier. This is a rectifier input. So this is a rectifier input, rectifier input. Okay, that means it was a rectifier output which has taken as input over here. So a rectifier output was a pulsating DC, pulsating DC. Okay, so for a full wave R rectifier, you can see that the output was something like this. This was the output for full wave rectifier. Okay, now this is your with respect to time, and this is your current or voltage, anything you can take, or you can take this as voltage also. Okay, now when this is passed through a parallel capacitor, so here you can see a parallel capacitor to the load. This is load resistance. Okay, load resistance. So parallel a capacitor, when the component is flowing, so here you are having pulsating DC, pulsating DC. That means you are having DC along with AC component. Okay. Now whatever AC is there will be passed through the capacitor to the ground. So, okay. So AC will be passed through the capacitor to the ground, because as we have seen, it will provide low reactance, low opposition to the flow of current in case of frequency increase, that is AC, and it will have high impedance when the frequency is low, that is DC. That means from this pulsating DC, whatever AC component was there, that will pass to the ground, and what remains will be a pure DC which will reach the load, and that DC which reaches the load, that I into R will give you this VL voltage. So this is nothing but I into RL. Okay, this is a pure DC what you will get at the output here. Okay, this is one way of explaining it. The other way of explaining it is a capacitor, for every half cycle, it will charge to the peak value as shown in the waveform here. So here you can see in this waveform. So here you are having your capacitor charging to the peak, and whenever there is no output of the rectifier, it will give a discharge. It will give a discharge. Again, when the next half cycle comes, it will go charge, it will go to the peak value. That means the value of the voltage remains between VL min and VL max. Okay, VL min and VL max, and that is you have reduced the AC component. It is always at some fixed value at the output of the peak, and therefore we can call it as a pure DC of the output of filter. So this filter can be used at the output of rectifier, so that the pulsating DC output of rectifier is converted into pure DC. Now this is called as a capacitor filter or C filter, where you have only a capacitor which is connected in parallel with the load. Okay. Then if you see the note of explanation, then you can explain it in this way. Same thing, as a capacitor allows AC through it and blocks DC, a filter called a capacitor filter can be constructed using a capacitor connected in shunt. Shunt means parallel, as shown in the figure. The rectifier output, when passed through this filter, the AC components present in the signal are grounded through the capacitor, which allows AC component to go to the ground, and the remaining DC component present in the signal are collected at the output, which will reach the load. This is what we had explained when we saw the circuit of C filter. Then we'll go to see the next type of filter, which is called as pi filter. Okay, so you can see that Greek letter pi over here. So here you can see the Greek letter pi. So that pi is like the shape of the filter. This pi, whatever we are going to write here, this pi is like a shape of the filter. And the shape of the filter will come as you will be having a capacitor, you will be having a inductor, and you will be having another capacitor. So this type of circuit will be called as a pi type filter. This is C1, this is L, and this is C2. Okay, so this type of filter will be called as pi type filter. Clear? Now here, pi type filter consists of a shunt capacitor that is parallel a capacitor at the input, which is called as C1 here, and it is followed by an L section filter where L inductor is there, and then you have another capacitor which is across the load, which is C2. Okay, the pulsating DC output voltage is filtered first by the capacitor connected at the input side, and then by a choke coil. Choke coil is inductor coil, and then by another parallel capacitor, that is shunt capacitor C2. Clear? The a construction arrangement of all the components resembles to the shape of a Greek letter pi, and therefore it is called as a pi filter. So if you see the circuit of this filter, you can see the rectifier output is given. The rectifier output is given at the input of this filter. So this is nothing but your pulsating DC. Okay, pulsating DC, which is this type of quantity where you see plus positive half cycles. So once this quantity enters here, okay, positive half cycles, that is pulsating DC is entering here. Now whatever AC component is there, it will first pass through this C1 capacitor to the ground point, to this point, and only DC will be passed here. Okay. Now in that DC which is passed here to the inductor, if there is any AC component present in that also, that will be blocked by this inductor, and more pure DC will come here. Okay. Now in that DC also, if there is any AC component, that AC component will go through this capacitor to the ground, and more pure DC will come at the output here. Okay. That means this input will be converted into an output of this kind. Okay, so this input will be converted to an output which looks like a straight line. This is like a straight line, so this is a pure DC. Ideally it is a straight line which is pure DC, and practically you can just have little variations there, so you can call it as a more purer DC than what was the rectifier output. Okay, that will reach the load, that will be the current I, and that current I multiplied by this resistance will give you the load voltage VL. Okay, so this is another way of reducing the AC component in the pulsating DC of the rectifier. So after rectifier in the power supply, you should use a filter so that pulsating DC is converted to a pure DC. Okay. Then if you see the working of pi filter, if you want to write a note, you can say that in this circuit, we have a capacitor in parallel, then an inductor in series, followed by another capacitor in parallel. Okay. Capacitor C1, this filter offers high reactance to DC and low reactance to AC. This is a basic statement. After grounding the AC components present in the signal passes to the inductor for further filtration. Then comes the inductor L. This inductor offers low reactance to DC component while blocking the AC component if any got managed to pass through the capacitor C1. Similarly, then one more capacitor is there, C2. Now the signal is further smoothened using this capacitor so that it allows any AC component present in the signal which the inductor has failed to block. So filtration is done three times, first by C1, then by L, then by C2. And then a desired pure DC output reaches the load. Okay. So uh, thank you students. This was my video on filters and the types of filters used in power supplies. So we have seen C type of filter and pi type of filter in this. If you are having any doubts over here, you can give me a call or you can send me on a WhatsApp, or you can also write a comment on this video, and then so that I can clear your doubt. Okay. Thank you, students.